Alright, let's look at the Laplacian. Alright, so notation is they can use, sometimes we use the this triangle symbol or nabla squared, which means that the dot product will be between nabla. Right, so let's compute this. So Laplacian is just divergence of the gradient of the function. Right, so you have natural log of x squared plus y squared. Right, actually let's use blue here. Alright, so let's compute this. Alright, so I'll do this divergence later. So we have to take the gradient of natural log of x squared plus y squared. So that will be just partial with respect to x would be x squared plus y squared on the bottom, and root of that is 2x. And then x squared plus y squared on the bottom, and partial of that with respect to y would be 2y. Right, then we take the divergence. So partial of this with respect to x would be, let's see, so we do the quotient rule. Alright, so square the bottoms guy, so x squared plus y squared. Alright, derivative of the top would be 2, and times the bottom guy, so you have x squared plus y squared, and minus, alright, oh, that would be square there. Alright, top, so 2x times derivative of the bottom with respect to x, so it's going to be 2x. Alright, so what you get is, actually, then we have to plus. Alright, then you have partial derivative of the second guy with respect to y. So we have x squared plus y squared, right, squared. Derivative of the top with respect to y would be 2 times the bottom, so x squared plus y squared, minus top guy is 2y, then multiply by derivative of the bottom, so it's 2y. Alright, so what you get is going to be, so everyone seems to have 2, so I'll put 2 in front. Alright, then the common denominator we already have, x squared plus y squared, quantity squared. Alright, then what you get is, let's see, so you have x squared plus y squared, and 2 is out, minus 2x squared. And then you have a plus x squared plus y squared. And then you have a minus 2y squared. Right? Then you can see that that's actually kind of nice. X squared, oops. Let's use a different color. You have x squared and x squared minus 2x squared cancel out. Y squared and y squared minus 2y squared cancel out. You actually ended up getting 0. Alright, so the Laplacian of this function happens to be equal to 0. Right? So another note that when the Laplacian is equal to 0, what does that mean? Right? So let's, in a general case, let's look at the Laplacian of f. F. So gradient would be partial of f with respect to x, comma, partial of f with respect to y. Right? Just let's do 2 variables. It's easier. All right, then take the divergent. Divergent is going to be second partial of f with respect to x plus second partial of y f with respect to y. Right, and this is equal to 0. Right, so what it's saying is that the second derivatives in x direction and a y direction is going to be either all equal to 0, which means that the surface is going to be flat, but different concavity. So one's concave up and the other one has to be concave down. So for example, in x direction could be positive, which means that it's a concave upward in the x direction, but this should be negative, which tells you that it's a concave downward in the y direction, right? So this equation, Laplacian being equal to 0, is used for something like a minimal surface. So for example, if you have a soap film, let's say, and you have a wire and dip that in a soap film. Let's say you have a wire which looks kind of like this, right? Then you dip that into a soapy water, and let the soap film to form, right? Then what happens is the Laplacian equal to 0 is a good way to describe this the surface, because what happens is that a surface is trying to contract itself to the smallest possible area. So for example, if you think of a surface that goes like this, like a cone, right? Then you can see that this is not going to be a ideal shape for soap film, because we can actually kind of push it down to make it more flat. So the more the ideal soap film will be in this case with this same boundary would be a flat one, right? So we don't want the concave downward throughout or concave upward throughout. So the best way to do it is having a kind of a saddle shape everywhere. For example, if you have a boundary, so you form it with a wire, and I put a soap film. So soap film is going to form something like this, right? So if you just focus on just one point, this is true for every point, but here, at this point, in one direction, you have a concave up shape. To offset that, you have on the other direction, there's a concave down shape, right? So the Laplacian equal to 0 can kind of describe this saddle point behavior, because we have to make sure that the sum of the second derivative equal to 0, which means that the one's positive, one's negative, unless they're both equal to 0, which means that the one direction you have a concave up behavior, the other direction you have a concave down behavior. So looks like a Pringle, right? Pringle, it kind of mimics the shape of the soap film, which is a minimal surface, right? But anyway, so this is a good example of Laplacian equal to 0, which describe sort of a minimal surface or surface of a soap film. Right? That's it. I hope that this was clear.